Keith, should be all yours. Thanks.
All right, yep. Thanks, JB. Let's see here. All right, so if you can't see my screen, just let me know. As JB mentioned, this was work that Jason and I completed when we were at North Carolina State University over the last couple of years. And I'm going to just start with a little background of high shear low CAPE environments and how we got here to this particular study. In a 2006 study from the STAR Prediction Center, Schneider et al. Defined environments characterized by these given criteria as the second key subclass of severe weather in the United States, which actually accounted for more significant tornadoes than the conventional plains environment, which was characterized by CAPE greater than 2,000 joules per kilogram. And in fact, over half of all significant tornadoes occurred in environments where mixed layer CAPE was less than 1,000 joules per kilogram, and 0 to 6 kilometer shear was at least 18 meters per second, or 35 knots. But despite their commonality, two subsequent studies from the Storm Prediction Center indicated that tornadoes within these high shear low CAPE environments occurred outside of tornado watches more often than tornadoes occurring in other environments. So a high miss rate with these high shear low CAPE tornadoes. So this is an example radar presentation of a high shear low CAPE tornadic cell. A few things to note here. First, you can see there is just a general smaller horizontal scale than what you're used to. Just a very brief increase in azimuthal shear, very brief but strong couplet as well. And just in general, the smaller horizontal and vertical scales within high shear low CAPE environments contribute to reflectivity signatures that are subtle. They can be non-classical. This doesn't really look like your classic tornadic radar cell. And they can also be transient or quickly developing. In addition, because these environments are highly dynamic, the convection is fast-moving, and radar-indicated rotation can be weak compared to your more classic severe convection, especially plains supercells. And this is particularly a problem at great distances from the radar due to your poor radar sampling of the compressed convection. And although it's not shown here, there's also often an absence of cloud-to-ground lightning. And all of these factors combined create for challenging warning operations in high shear low CAPE environments. So the first objective of this research was to improve the forecasting of high shear low CAPE significant severe environments. And only a few studies conducted over the last 15 or 20 years or so have really focused on severe high shear low CAPE convection. So to address this forecasting challenge, we wanted to first assess the utility of existing techniques and composite parameters such as the significant tornado parameter, the energy helicity index, and so forth within high shear low CAPE environments. Following this assessment, we then explored our own development data sets to determine what environmental parameters are most skillful at discriminating between significant severe and non-severe convection. Then by combining these individual parameters into a composite parameter, we were able to show a statistical improvement in skill over all of the other composite parameters we tested. So we're going to discuss this and other benefits of the SHRB, or the severe hazards in environments for the reduced buoyancy parameter, in high shear low CAPE environments, particularly those associated with low LCLs, and we'll discuss a couple other potential environments later on. And the second facet of this study focused more on the nowcasting of severe high shear low CAPE environments, particularly in terms of the radar-based warning decisions. And Jason spent a great deal of time investigating vortices within high shear low CAPE environments, including tornadic and non-tornadic mesovortices, in addition to tornadic mesocyclones within mini supercells or embedded supercells. And he especially focused on identifying key features or trends in radar-derived products leading up to mesovortex tornado occurrence, and how those varied in the non-tornadic mesovortices. Additionally, he compared and contrasted tornadic mesocyclones within mini supercells or embedded supercells against mesovortices that produce tornadoes. And finally, Jason worked on climatology of the high shear low CAPE reflectivity signatures to determine their utility and limitations in the warning decision process. So, in terms of our definition of high shear low CAPE, we use the same 0 to 6 kilometer shear threshold as the Schneider et al. Study, with the at least 35 knots or 18 meters per second over the 6 kilometer layer, surface 6 kilometer layer. In terms of CAPE chose 500 joules per kilogram with a surface-based parcel, and this was because operational forecasters noted based upon experience that, first of all, environments characterized by CAPE greater than 500 joules per kilogram should be expected to support possibly significant sphere convection, given high shear, low convective inhibition, and also adequate forcing. Additionally, radar signatures tend to exhibit more classical characteristics, even if they were on a smaller scale, when CAPE exceeded about 500 joules per kilogram. So that's why we used the 500 there instead of the 1,000 that's used in previous studies. In terms of the nulls for this study, those were defined as a severe thunderstorm or tornado warning that was issued when no severe reports occurred in that given CWA for the entire day. And these nulls simply represented non-severe convection and were compared to our high shear CAPE significant shear reports in our statistical analysis. And then for all significant shear reports and null points, archived SVC mesoanalysis data from the nearest grid point and the previous hour were utilized. So most conventional composite parameters, be it the SCP, spread cell composite, EHI, so forth, they all have CAPE as a primary ingredient. So as a result of this, they struggle to adequately represent risk in high shear CAPE environments. So in developing a new parameter, we wanted to use more of a statistical approach with no preconceived notions about what parameters may or may not exhibit skill. So basically, we tested all parameters indiscriminately. And throughout our statistical analysis, we primarily utilized the true skill statistic, or the TSS. And TSS includes hits, false alarms, misses, and also correct nulls. And these correct nulls are very important for testing forecasting parameters, as forecasters must be able to trust the parameter when it suggests a non-event just as much as when it predicts a significant sphere event. And it's important to note here that our entire data set was associated with ongoing convection, either significantly severe or non-severe convection. And as a result, these parameters can't be used to forecast the development of convection, but only to forecast the potential severity of convection that's expected. So our findings must be used in association with situational awareness and a confident convective forecast. Otherwise, basically what we've seen in terms of what we've been observing with our test cases of the Shear parameters is that you can often get false alarm areas where you wouldn't expect convection. So you have to be cognizant of that and only utilize these parameters where you expect convection. But ultimately what we did is we combined the three conditionally most skillful parameters into a product designed to reduce false alarms while still optimizing the probability of detection of significant sphere reports. And our new forecast parameter, the Shear, it has a familiar formula. It's a product of instability and shear parameters, which many composite parameters are made up of. But instead of CAPE, it uses lapse rates, both the low-level and mid-level lapse rates here. And these lapse rates have been shown in previous research. As they become steeper, they tend to correspond to a higher risk for all threats, be it tornadoes, winds, or hail, and particularly when you're dealing with low-level lapse rates, that's the case. And another advantage of lapse rates over CAPE is they're generally less prone to errors than your integrated instability measurements. So CAPE values, less than 500 joules per kilogram, which is within our high shear low CAPE threshold, they're actually within the margin of error for SBC CAPE mesoanalysis and also hourly RAP forecasts. So because of that, lapse rates are probably more advantageous in these marginally unstable situations. And then in terms of the wind or shear parameter that's used here, we're focusing on two different ones, the 0 to 3 kilometer shear version and also the effective shear version, which seem to be the most skillful compared to all of the potential combinations here. The shear parameter that you should use is really conditional based on regime, region, season, and so forth. Actually, for the wintertime significant wind events, the 6-kilometer wind magnitude combined with these lapse rates was actually the most skillful, and that was probably due to its correlation to system propagation speed and momentum transfer. But in general, the Shear S3 and the Shear B seem to have the most utility across a broad range of high shear low cape regimes and regions, and also seasons. And in terms of these normalization values here, the elapsed rates are normalized by their optimal thresholds, and then the shear magnitudes are normalized by a value that makes the entire parameter optimized at a value of 1. So I'll get into a little bit more on that shortly, but in terms of the 0 to 3 kilometer shear and effective shear, the 0 to 3 kilometer shear has been cited in previous work on QLCSs, particularly in terms of promoting strong sustained updrafts, so that goes all the way back to RKW theory, in addition to stronger mesovortices and overall a higher threat for tornadoes. The effective shear was actually designed with this shallow convection in mind, which is common in the high shear low cape environments, and also with elevated convection in mind. And that was because 6-layer shear parameters were really deemed insufficient to adequately provide a representative shear layer in these environments. The one caveat here with the effective shear version, effective shear is inherently dependent on cape. So in situations where you have errors in cape, or the cape is just very small, it may be poorly represented in these environments. So the 0 to 3 6-layer version may be more stable in those especially low cape cases. They're especially marginal within that margin of error. And in fact, some of the significant SEER reports in our development data set were associated with data points that had analyzed 0 cape. So in those situations, obviously the Shear B would go to 0, but you could still get some utility out of the Shear S3 here. Now this is a plot here with the true skill statistic on the y-axis and different threshold values for the given parameters on the x-axis. And first of all, the true skill statistic is essentially the difference between the probability of detection and the probability of false detection. And this plot shows, as I mentioned, TSS, y-axis, threshold value on the x-axis. So here I mentioned that the Shear S3 and Shear B were designed to have optimal thresholds of 1. So you can see their maximum TSS is at a value of 1, and it will decrease downward with lower values and also upward with higher values. And basically what this means is at that value of 1, you have the greatest separation between your significant severe reports and your non-severe reports, or non-severe points of convection. And so there are two primary items of note here. First, the Shear S3 and Shear B do clearly outperform the existing composite parameters at discriminating between high shear low cape significant shear reports and nulls within our development data set. And this is made up of reports and nulls in the southeast and the mid-Atlantic. And secondly, although parameters such as the STP and EHI do exhibit skill, their optimal thresholds are well below their conventional threshold of 1. And in fact, STP's optimal threshold is actually around 0.2. It's kind of tough to tell on this graph. But it's around 0.2, which is below what is currently operationally contoured on the SBT mesoanalysis. So that's also something you have to be cognizant of if you're going to be using these other composite parameters. In high shear low cape environments, you may have to look at values lower than what you're used to looking at to actually get any utility out of them. And this plot here compares the maximum skill of the 7 tested composite parameters across several regions, and we just had some kind of user-defined regions here by lat-lon. But basically what to note here is that the Shear and Shear B do outperform existing composite parameters in the region, including our CSTAR domain, which would be the lower Mississippi Valley and the South Atlantic. But these parameters also outperform other composite parameters in pretty much every other area, at least one of them, either the Shear S3 or the Shear B, be it the Northern Rockies, the Southern Plains, Eastern Great Lakes, what have you. The Shear S3 or the Shear B is the most skillful. And granted, some of the sample sizes in these regions are fairly small, especially the ones that aren't shown on this particular plot. So there's less confidence in the statistical significance of these results as you get to lower sample sizes. But regardless, these results are promising, and they do indicate that the lapse rate shear product is quite robust with high Shear Cape environments. And there is somewhat of a regional variability to skill, both in the churred parameters and also the other composite parameters. And this is more than likely representative of two primary high Shear Cape regimes, the low LCL cases with the moist boundary layer, which are common really in the lower Mississippi Valley, South Atlantic, and Ohio Valley in general, and also high base cases where you have deep weld mixed boundary layers with a narrow sliver of cape above that. Those would tend to be more significant wind cases, but those are to be considered. That's especially an issue across the high plains and also the western U.S. And actually in our initial data set, we also included elevated cases which met our surface-based cape and shear thresholds, but had higher values of most unstable cape. We've since cut those out by using a mu cape threshold of 1,000 joules per kilogram. So while there's still maybe some of what we would consider elevated cases, especially in the northern plains and upper Midwest, most of those have been taken out of this latest data set here. And in terms of looking at box and whisker plots, they do reveal clear separation in the distributions of the Shear S3 and the Shear B between significant tornadoes and nulls in the nationwide verification data set. And just in general, approximately 75% of significant tornadoes had a Shear S3 above 1, while 75% of the nulls had a Shear S3 below 1. And the same could be said here for the Shear B distributions. So as shown in the preceding slides, although parameters such as the STP and EHI do exhibit skill at discriminating between significant severe reports and nulls and high Shear Cape environments, their thresholds must be lowered, often beyond the values that are operationally contoured on platforms such as the SBC mesoanalysis, for example. On the other hand, both the Shear S3 and Shear B show a consistent optimal threshold near 1 in these high Shear Cape environments. And actually, even looking outside of high Shear Cape environments, the Shear B especially seems to have some utility as its optimal value remains around 1, even when you look at all environments, not just high Shear Cape environments. And the Shear S3 in particular is very skillful in dealing with these service-based low LCL cases, which do include the majority of high Shear Cape significant tornado events in the southeastern U.S. And again, going back to the box and whisker plots, the majority of high Shear Cape significant shear reports did occur with Shear S3 and Shear B values over 1, and the greatest discrimination from both parameters was when comparing environments that produced significant tornadoes to those producing non-severe convection. So in terms of the availability of the Shear S3 and the Shear B, the Shear S3 is now available in AWIPS. In terms of the volume browser, it's currently only available in AWIPS 1. They're still working on getting the AWIPS 2 version implemented. And JB might be able to add some additional detail once I'm finished here when I'm handing off to Jason. But in terms of GFE, the Shear S3 is available in AWIPS 1 and 2. Matt Parker, one of the PIs here in the CSTAR grant at NC State, does have real-time plots of the Shear S3 and also the Shear B now, and those are available for the RAP, NAM, and GFS. We've been in talks with the SBC for quite some time about adding the Shear S3 to the mesoanalysis and also the Shear B, I believe. This is still a work in progress, but as I understand it, they are testing the Shear S3 and the Shear B on an internal page, and they're looking to make that operational at some point in the near future. And we've also been talking with some folks with HSLC, the HER, discussing the possibility of including the Shear S3 and Shear B on that platform. But from what I understand, it hasn't gotten too far yet, so JB may be able to add a little bits of additional information. But anyway, I will hand it off to Jason now, and JB, if you want to chime in on this particular slide while I'm doing that, go ahead.
That's fine. Thanks, thanks, Keith. You summarized it well. We're pretty confident that it'll show up on the HPC meso-analysis in the near future. We think that's pretty much a given, just they need to take care of some things there. They may, because they still want to evaluate it, may not put it on the typical meso-analysis page that we're used to, but may have it kind of hidden in a spot just as it's being evaluated. And once we get details on that, we'll be sure to share those. And the AWIPS 2 issue with displaying the data, we're still trying to shake that out here. We're a new AWIPS 2 site, and just want to make sure we have everything taken care of before we push that out. But that should be coming as well in the not too distant future. Looks like Jason is ready, and I'll hand it off to Jason as we'll be talking more about some radar-based work that he's done. And I'll hand it over to you, Jason. Thank you.
Hey, Jonathan?
Yeah.
Yeah, Ken Johnson, Eastern Region. Can we ask questions now, or do you want us to wait?
Why don't we hold questions to the end and let Jason give Jason a chance to finish up? It should be another, I guess, 15 minutes for that. And out of respect to him, why don't we do that?
No problem.
Okay, for the radar-based climatology, our main goal is to look for ways to distinguish between tornadic and non-tornadic supercell mesocyclones and QLCS vortices, which at times I'll refer to just collectively as vortices. And a few other areas that we'll break them out separately. There's two main parts to this part of the project. First, what can we learn about these storms in velocity data? And second, what can we learn about them in reflectivity data? So starting off with the velocity, the main parameter we looked at was NSSL's linear least squares derivative azimuthal shear product. So a new product that uses velocity data from multiple points to calculate azimuthal shear, and not just the velocity peak, as some other calculations do. It's not something that can be hand calculated, but it's done by an algorithm. And it's a product that should be available in some of the new multi-radar, multi-sensor data. And an example of azimuthal shear is shown here. On the left, you can see a strong couplet in rate of velocity that corresponds to a local maximum in azimuthal shear of around 0.02 per second, which would be a fairly high value. And we developed a population of tornadic and non-tornadic vortices. Included 95 unique tornadic vortices. These were from confirmed tornadoes. And also 135 unique non-tornadic vortices that were associated with false alarm tornado warnings. So we looked at vortices for which tornado warnings have been issued, but no confirmed tornadoes were found along the path. And all these cases occurred in the southeast in high shear located environments between 2008 and 2011. And the main thing we looked at was, again, azimuthal shear to quantify the strength of the radar observed rotation in these vortices. Next few slides will be showing some composite time series plots of azimuthal shear, and so I quickly wanted to orient you to how these plots are laid out. We put the azimuthal shear data for all the vortices into a tornado relative time coordinate system for the tornadic vortices, and a false alarm warning relative time coordinate system for the non-tornadic vortices. So the center of these plots then will be, or t equals 0, would be the time the tornado formed for the tornadic vortices, or the time that the first false alarm warning was issued for the non-tornadic vortices. And so then times to the left and right of that will indicate times before or after the tornado or warning. And it's important to keep in mind these plots that it's going to be less samples as you go farther backward and forward in time from the time of the tornado or warning. And so at t equals 0, you'll have the most samples, and different vortices with different lifetimes, of course. And so those numbers will trail off as you go further backward and forward in time. So just keep in mind these plots that any trends at the far right or far left of the plot could just be noise. So green indicates azimuthal shear for the tornadic vortices, while red indicates azimuthal shear for the non-tornadic vortices. Then median values of acceptable shear are indicated by solid lines, and then the interquartile range is filled. So that'd be the 25th to 75th percentile values of acceptable shear for the population. So if you're familiar with the box and whisker plot, that would be kind of the box section of that kind of plot, but then showing how that changes over time. I put filled circles at times when we found statistically significant differences in median acceptable shear between the tornadic and non-tornadic vortices. Filled circles means the difference was significant at the 95% confidence level, while open circles indicate a 90% confidence level based on the calculated p-values. So here are the main results from this section of the research. We'll focus today only on vortices that happen within 60 kilometers from the radar. So pretty close, as that's where we found the best results. And so the top is showing results for the supercell metacyclone cases. The bottom is showing results for the QLCS vortex or non-supercell type cases. And so starting out in the top left corner, you can see at the base scan or the half-degree elevation angle, well, the tornadic supercells did have a little bit higher acceptable shear than the non-tornadic supercells at the time of the tornado. That difference was not found to be statistically significant. However, interestingly, in the bottom left, we looked at the base scan for the QLCS vortex cases or non-supercell type cases, and we actually did find statistically significant differences in acceptable shear between the tornadic and non-tornadic vortices, starting about 5 to 10 minutes before the tornado. Also, we found kind of 0.01 per second being a good general guidance or threshold value of acceptable shear to look at. If you look up a couple tilts higher into the vortex around the 1.8 degree elevation scan, though, you see that any significant differences at the time of the tornado go away a lot. And for both supercells and non-supercells, the tornadic and non-tornadic vortices had similar acceptable shear a lot. And once we looked at vortices more than 60 kilometers from the radar, we found no significant differences between the tornadic and non-tornadic vortices. And that's due to effects of both beam height and beam filling. And especially since we saw differences only near the surface close to the radar in the lowest 1.5 to 2 kilometers, it seems that the main issue further from radar, of course, would be not being able to see near-ground rotation. And that's definitely a challenge, as only 20% of our southeast domain is within 60 kilometers of the radar. We also know it's close to the radar, clear significant differences between tornadic vortices that produce EF1 and greater tornadoes versus non-tornadic vortices. Some clear significant differences, and of course these are EF1 and greater tornadoes pose the greatest risk to life and property, as well as having a more robust record of their occurrence. Well, one caveat to this result, though, is that the majority of our EF1 and greater tornadoes close to the radar actually happen to be from QLCSs. Next, we'll move on to the reflectivity signatures climatology. We'll look at several different signatures, many of which are pretty common, but a few are not as common as we've looked at. And I established criteria for these and manually identified them in association with the tornadic and non-tornadic vortices. I identified these signatures within a window that started 20 minutes prior to the tornado for the tornadic vortices, or 20 minutes prior to the first false alarm warning for the non-tornadic vortices, and then ending 15 minutes after this time. For supercells, the two main signatures that we looked at were hook echoes and the presence of either a bounded weak echo region or a weak echo region. And in these plots, the green lines indicate probability of detection, or how many of the tornadic supercells had this signature. Red lines are probability of false detection, or how many of the non-tornadic supercells had these signatures. And the black dashed outline is false alarm rate, while the blue dashed lines are median lead time for when these signatures first showed up relative to the tornado. And then these plots show how these parameters change as you get further away from the radar. So within 100 kilometers of the radar, both hook echoes and weak echo region had pretty high probability of detection. around 80 to 90%. But the problem is the false detection were just as large, which is not surprising, as many supercells will have hook echoes in the Decker regions, and of course many supercells are not tornadic. And so that resulted in false alarm rates around 50%. Median lead times for when these showed up with a tornado, though, were around 15 minutes. Looking to the far right of these plots, though, once you got more than 100 kilometers from radar, the POD and the POFD for both these signatures dropped due to the radar sampling issues of beam filling and beam height, making it hard to discern these features. That's especially a problem in high shear locate environments, given that the supercell drops the low tops for many supercells. For QLCSs, there's four main signatures that we looked at. First, we looked at reading flow notches in the small line on the top left. On the top right, little Boeing segments in the expected line, such as in a line echo wave pattern. The bottom left of the signature we noticed, some of our cases where we noticed kink or an inflection point in the gust front in the velocity data. And then I'll go back to the Brook Nest signature in a little bit. So these first three signatures, the rear inflow notch, the Boeing segment, and the gust front cut, again, close to the radar within 50 kilometers. We found pretty high probability of detection with these signatures of around 80 to 90%. But again, the probability of false detection were also fairly high, especially for the rear inflow notches. So they were a bit lower, closer to 50 to 60% for Boeing segments and gust front cuts, which helped to lower the false alarm rate for those signatures down to 35%. But the median lead times when they showed up relative to tornado was only a few minutes. And then again, as we get further from the radar, the POD and the POFD, so these signatures dropped off as it became hard to see these signatures farther from the radar. Signature in the bottom right is the broken nest signature. It's something that's been identified by a few forecasters in the southeast in a few case studies. There hasn't been a more broader study to see how often they actually occur. And this was actually present in the loop that was shown in the beginning of this presentation. And what happens in these situations that's been noticed is that a break occurs in the convective line where the southern segment surges ahead of the northern segment, and a tornado has been shown to form sometimes near this break in the line. For our QLCS cases within 60 kilometers from the radar, we found the Brook Nest signature in about 35% of those cases, and a little under 30% of the non-tornadic QLCS cases, with lead times typically being 0 or negative. Interestingly, at medium ranges from the radar, or 60 to 100 kilometers, we actually found a signature with over 60% of the tornadic QLCSs, and actually none of the non-tornadic QLCSs, with some lead time. But we don't yet have a good explanation of why this occurred, and more study needs to be done with more cases. So some of the main takeaways from today's presentation are that high shear locate severe convection is a forecast problem everywhere with a variety of different regimes, such as elevated and high base cases. But today we focused on the low LCL cases, which are most common in the southeast. We introduced two new composite parameters, the Shear B3 and the Shear B. It's important to remember that these do not forecast the occurrence of convection, as you may see them both threshold in an environment where you don't expect convection. But what they're for is that once we do expect convection to happen, they can help forecast the significance of the convection. And the Shear B3 and the Shear B improve on existing composite parameters, discriminating between high shear locate, significant severe convective, and null environments. And the key thing of these parameters is they focus on using last rates of shear magnitude rather than case, which other composite parameters, such as the tornado parameter, are used. And this case calculation can be volatile, such as with different errors possible. Using lapse rates is found to be a little more robust in these types of environments. For the radar part, we found that azabal shear discriminated well between tornadic and non-tornadic vortices within 60 kilometers of the radar, especially for the QLCS as a vortice cases. But farther from radar, we found no difference in the magnitude of the tornadic and non-tornadic vortices vortices. I didn't discuss lead times much in this presentation. We did see some potential for longer lead times for as-well shear for supercell cases, but not for the non-supercell QLCS cases. Some key reflectivity signatures were found to have high probability of detection, but also high false alarm rates. And radar sampling properties are found to be a very critical factor in what forecasters see, and its range from radar was very important in the results. And forecaster knowledge of the typical diameter, altitude, and intensity values for the tornadic vortices can help them to consider what will or won't be detectable at various ranges. All in all, with these results, reflectivity, velocity, and environmental data all need to be used together in conjunction with one another for warning precision purposes, and there is no silver bullet. Both Keith and I have both been working on some journal articles for weather and forecasting. They have actually both been recently accepted for publication, and so those should be showing up on the AMS website in the near future. I'd like to acknowledge our funding from the NOAA National Weather Service CSTAR program and AMS graduate fellowships, as well as an NSF grant. And I want to acknowledge all the hard work of our fellow collaborators and also the help we've had from the Soil Prediction Center. With that, we'll leave our contact information up here, and I'll turn it over to Jonathan to open up for questions.
Thanks, Jason. I appreciate that. And we certainly have time for questions. And Ken Johnson, if you're still with us, you guess you're first up.
Oh, thank you. Good presentation and good work by you all. Yeah, Jonathan, I guess the question is more for you in a statement you made a little bit ago about, I think you said HPC was going to include this in their meso-analysis, and you said that they were, it was going to undergo further evaluation by them. I was wondering what the nature of that evaluation was, and you know, what you could tell us about it.
Yeah, so evaluation may not have been the best term there, but our understanding is they've got the coding all set up, and they actually are creating the analysis now, and they've been kind of viewing it in-house, I guess, for a little while. I think there's some reluctance on their part to rush out these kind of parameters on their website, so I think they've taken their time with that. To be honest, I don't want to speak for them, but I think the fact that the publications are now accepted, I think that probably adds a little bit more weight behind that. So I don't think it was a formal evaluation. Maybe they just wanted to let the path or the course, I guess, continue on and get closer to the end. Our expectation is that the coding is ready, and they just kind of need to get a couple of in-house things, get a couple people there at the same time to kind of make the switch. It is not likely to be on the regular drop-down menu part of the SPC meso-analysis page, so it may not end up right underneath the SIG-TOR parameter, for example, just because I think they still want to see some additional kind of case study or examples of it. Those are kind of things we promised we would keep in touch. Keith was at least one part involved, and he has made multiple visits to the Storm Prediction Center. He might be able to add a little bit more to that about some of their maybe concerns or feedback about the SHRB and the SHRB S3 and the SHRB.
Sorry about that. I still have my mute on. I haven't talked to them too much lately, but from what I understand from discussions with Matt Parker, I think they were concerned about one of the things we had mentioned during the presentation, which was the false alarm areas that you can get where you have the values above 1, above the optimal threshold, where you wouldn't actually expect convection. And they're kind of concerned about people potentially using that incorrectly and just not having a good knowledge of you know, those false alarm areas being there, but not ignoring them, basically. So we've been kind of working on some potential ways to mask those values, and actually on Matt's, the plots on the NCSU page, he's been working on some masking using most unstable lifted index values just to remove some of those false alarm areas. And we're, I think, slowly stepping towards getting towards the point where the folks there will be content at least making it available to the NWS forecasters in an internal sense. But like JB said, I'm not sure how long we'll have to wait for it to become really publicly operational if that ever does happen. But I do think that finally getting through the review process with that article is going to help.
Okay, thank you.
Any other questions out there?
Okay, Jonathan, I'll ask one more if you don't mind.
Yeah, go ahead.
There was a comment made towards the end of the presentation here about this not forecasting convection, but more or less giving an indication of the nature of the convection. And I was wondering if in that context, if you could comment in terms of the value or usefulness for situational awareness with your forecasters and how that may be helping your forecasters.
Yeah, I think well, generally when you evaluate the environment or the potential for severe storms, I would think you would first, and this is just speaking for myself when I do it, I mean, I would first analyze the entire scope of possibilities and have confident forecasts that you are going to be dealing with convection. In that situation, you can start looking at other parameters like the Shear, and even the other composite parameters like the significant tornado parameter. I didn't mean to, in the presentation, I didn't mean to say you shouldn't use things like the STP when you're dealing with high shear cape environments. I think it's advantageous to use that in addition to parameters such as the Shear. But I think, looking several days in advance, we've heard some examples of where the Shear has helped offices with staffing decisions, because in the past these high shear cape events would really kind of sneak up on offices just because, in general you do get a lot of hours where you're dealing with these high shear cape environments throughout the entire year. Most of them are not going to be severe, but every once in a while you do get severe or significant severe episodes with them. And just having a parameter like this that can help you identify maybe, a few days in advance they're going to be dealing with a situation like this that could potentially produce significant severe convection, be it on a small scale or a large outbreak. I think that's really one of the key benefits of a parameter like this. In addition, when you're dealing with warning operations, as Jason showed in some of his examples, I mean, there's really not a whole lot of difference, especially as you get farther from radar, between those cases that are going to produce tornadoes and those that aren't. And actually, there's an extra slide in the presentation that kind of shows, tornadic vortices, the time series of significant tornado parameter, of the Shear, and I believe another parameter. But basically, the STP, even when you have tornadic vortices, as it's going into that high shear, low cape environment from a high shear, high cape environment, that STP value is going to tank, even if it's going to still produce a tornado. Whereas the Shear value is pretty steady the entire time. So even down to the warning scale, I'm not going to say it's going to work in every situation, but just having a more smooth, I guess, field with the Shear S3 versus something like the STP, which is going to fall off when you lose your cape. I think that's going to be really advantageous for warning operations as well. And we've seen that in some of the case studies that the WFOs have presented so far. So I think it's both, the several days in advance and also the nowcasting where you can actually get utility out of this.
Okay, appreciate that response. Thanks again.
Mm-hmm.
This is Brian in Midland. Good presentation, guys. Do have a question and maybe a follow-up. Did your study capture any tornadic cyclone tornadoes?
Tropical cyclones?
Yeah.
No, we actually we purposefully took them out of the study.
Okay, good. Because that's what I was. That was my follow-up. Okay, thank you.
Mm-hmm.
Okay, we have time for a couple others if anybody has any questions.
Jonathan, this is Bob in Cleveland. The plots there with the shear and the time series with the tornadic cases, the second half of the presentation, it might be informative for the forecasters to see those plots also done with a rotational velocity as opposed to just shear on the y-axis, because most of our operations are, still we're looking at rotational velocity and trying to select color curves that are optimal for that. So I know we can compute shear, but it is a little bit more involved.
Yeah, in the article I do have some plots of delta V as well, and it was found to be maybe not quite as good as that with shear, but still there was some differences in delta V as well between the tornadic and non-tornadic vortices.
Bob, does that help? I know we had discussed that as a part of our group. Jason, in his paper, explains that. And you did that, I guess, was that computationally why you did that, Jason, for your algorithm? Is that why you chose azimuthal shear? Maybe you could describe that a little bit.
It probably normalizes, the vortices that way, I'm sure. But I'm just thinking operationally, if we're trying to use the diagrams we've seen today, operationally, you want to look at, some sort of thresholds there, certainly. At least attempt to have thresholds.
Yeah, no, we have some follow-up work which is being led by Justin down at Greenville Spartanburg, and he's working on something similar to that, I think, and some other materials, I guess, as a reference sheet maybe that is being put together. If I have that correct, I may not have my facts all correct there, but I can follow up with you, Bob, and we can try to put something like that together. Some of Jason's presentation, in some respects, was a little bit depressing, in that unless these events occur very close to the radar, you may be out of luck in many occasions, and there's not a lot we can do about that at this point. But there's some encouraging news, and that's with the arrival of sales on the with the new radar build coming, I guess, later this spring and summer, where we will at least get more frequent lower level or base scans once every minute or two, I guess, and that will help us keep track of some of these faster evolving systems, obviously. But if it's too far from the radar, then it's going to be problematic for sure.
Hey, this is Steve Zubrick. When we go to higher resolution models, like we've actually been looking at the NAM fire weather nest that's down to like 1.33 kilometers. If we were to calculate the SHER, from the higher resolution models, is there any dependency, with these equations and the value, greater or less than 1, with going to a higher resolution model where the model may resolve, say, narrower and higher values of some of these parameters, like 0 to 3 kilometer shear, et cetera?
That's a good question. So far we've been looking at the lower resolution GFS and NAM stuff in the NCSU plots, and also the RAP. I guess the RAP of those three has the best resolution, and you certainly see some differences between the three, whereas you do have more localized differences in the RAP. And if you've been looking at, maybe JB can chime in on this, if you look at GFE, you might have the same sort of thing where you have those localized differences. Personally, I haven't looked enough at the high-resolution data to be able to determine that. And the SPC mesoanalysis data we used was 40-kilometer grid spacing, so that's fairly coarse. So I think it'd be certainly advantageous to start looking at the higher-resolution data just to see how much utility we can get out of it. But that's something I haven't really been privy to just yet.
Okay, thanks.
One other follow-up to that, and I do think you're going to see a lot of noise in there, but I guess there's one break, and that is by using lapse rates, you're at least maybe potentially smoothing out some of the variances you may see by looking at something like CAPE, which maybe modulate even more by local differences in dew points and things like that. So that may tend to reduce that. But that would be interesting to see how that would evolve in an event and see if you could find utility in that. Those are great questions. Anything else before we let Jason and Keith go? Well, hearing none, I just want to thank both those young men for all their hard work. I know they've put in a lot of hours with this, and they've obviously finished their graduate work here with their master's work and have moved on to other things, at least temporarily. But they are certainly good quality guys who put a lot of hard work into this, and they have aspirations, to be involved still in meteorology and potentially with the Weather Service. And I want to thank them for helping us out and spending some time with us. And thank everybody else for dialing in and listening in. If you ever have any questions, the contact information was on the screen, and we'll share the PowerPoint and some other materials if you have questions for follow-up down the road. So thanks, everybody. I appreciate it.